So hello and welcome to the week 3 second part of the introductory lecture series on the R statistical programming language. I'd like to go back to some issues that I mentioned in the previous lecture, which I'd like to talk about in a little bit more detail here. And the first thing I'd like to talk about is what are called conditional operators, such as the greater than, less than, and equals and not equals, and greater than and equals, less than and equals. These are all what are called conditional operators. And I want to remind you of the property of R that when you apply a conditional operator to a vector, you end up getting what's called a logical vector in return on sort of an element-wise basis, answering the question, does this element of the vector meet the condition such as greater than a value, or does this element meet that condition? So on an element-wise basis, you're getting the answer true or false. Does this element's value meet that condition? So let's do a quick example here. We can create a series of numbers. Remember, just using the colon separator here. So let's create a vector called numbers. And now let's answer the question, which of these numbers is less than 5? So we have the is LT5 vector. And what we get in return is a vector of a logical vector. And one property that I'd like you to understand about logical vectors is that you can answer the question how many values in that vector are less than 5 or meet the condition simply using the sum function. So by default, when you use the sum function on a logical vector, you end up summing the true values in the logical vector. So this is a way of counting up how many values in a particular variable meet a condition, in this case less than 5. So we can do something similar here with what's called string equality. So if we're working with character vectors, we can apply a similar conditional and say bases, in this case a vector of A's, T's, G's, and C's, and say bases equals, again, same operator as numeric equals, A. And this would return a logical vector with trues at the positions where there is an A. And I'll let you play around with that and see if you can then count up the number of A's simply by using the sum function on is.addMean. Also like to introduce you to the common arithmetic operators in R. These are familiar. Obviously this one might not be. This is simply exponent here. So if we want to multiply, say, 10 raised to the third to the second power, you can use the double star operator. Logarithms in R by default are the natural log. You can set whatever base you want using the base argument to the log function. So one of the important principles to learn about R is that it's what we call a vectorized language. So this becomes obvious when we're working with vector arithmetic. So if we multiply the vector numbers times 2, what's going to happen is that the 2 is recycled and multiplied times all values in the numbers vector. So if we can convince you of that here by multiplying a series of values from 1 to 10, we can multiply them by 2 and end up with the expected result, where we've multiplied each element on a sort of element-wise basis by 2. So we can also do something a little bit more complicated here. I'll let you play around with this example where we try to convert Fahrenheit values into Celsius. We do that again with simple arithmetic, but these constants again get recycled so that this small equation here gets applied to each element in the Fahrenheit vector. Okay, so again, I'll let you play around with that, but in our terms, what this means is that we are recycling sort of these operations and doing them sort of on an element-wise basis. So we can also multiply, say, two vectors against each other. In this case, this is just multiplying this vector against itself, essentially, and the behavior here, as you might expect, let's take the shorthand here, is a vector of the same length, and what we are seeing is that the first element of each vector is multiplied by itself. The second element of each vector is applied by this, multiplied together, and the third element of each vector multiplied together. So, just a heads up, what happens when you multiply vectors of different length, and this leads to recycling of the shorter vector. So I'll let you play around with what happens here, but what happens is that 1 through 10 gets multiplied the first by a series of numbers 1 to 5. What happens is that the first 5 numbers of the 1 to 10 vector get multiplied as times the 1 to 5, and then the second series of 5 numbers in the 1 to 10 vector get multiplied by 1 to 5 separately. So this is again called recycling. It's effectively the same thing as when you're recycling a constant, in which that constant is being applied to each value of this vector separately. Here we're simply recycling this vector. Let's give you an example just so that it's a little bit more concrete. So one of the second shorter vector, notice here first of all that we're getting a new vector of 10, which is the length of the longer vector. And we have the first value is 1 times 1 is 1, then we have 2 times 2 is 4, 3 times 3 is 9, etc. But then when we get to the second series of 5 numbers, we recycle and we go back to 1. So it's 6 times 1, 7 times 2, 8 times 3, etc. Just something to be aware of as you go along working in R, both in this course and beyond. And now another thing I want you to be aware of is that, again, remember that matrices are really just two-dimensional vectors, and so as you might expect, then the behavior of here is quite similar to the behavior of multiplying two vectors together, and I'll let you play around with this example. Now, one of the other things that I want you to be aware of in this class is how what are called logical operators work. So a logical operator here illustrated by the and or ampersand, which is an and the vertical bar here, which is an or. So this is a way of combining logical vectors, and this is ultimately the way in which you can create quite complex sort of queries to extract values that meet desired conditions when you're working with large data frames, which we will be doing in this class. So let's take a simple example here where we have two logical vectors where I've simply physically put in the trues and falses here. Again, notice no quotes around the trues and falses. So these are logical vectors. So what positions are true in the first and second vectors here? Okay, so we can look at that. So which are true in either? Okay, so first position meets the condition, the second position meets the condition, the third does not, the fourth does. So how do we code that in R to return a third logical vector that has two trues, a false, and a true? Well, the answer is that you use the logical operator or. Okay, so logical.1, logical.2 with the or operator in between. So let's just do that quickly. Reconstruct this example. sure I'm doing this correctly. Actually, I had it set up like this. Okay, here are our two logical vectors. Now we want to know, once again, which elements of these two vectors are true in one or the other of the two vectors. And so what we can do here is do logical.1 or logical.2, and this is going to return a third logical with the desired conditions. So this is really important skill to learn. It's something that's important to understand. We can also do something similar and say which are, true in both, okay? And the answer is, so if we use and, so that means true in both of the two vectors, and there's none, okay? So none of the positions have a true in both vectors, okay? So we get false across the board. So one thing that's important here then is to say, let's use this now in a practical sense where we want to say take a vector of numbers, okay, here, 1, 2, 5, 13, 22, 23, and 29, and we want to apply sort of a more complicated set of conditions and say we want to extract the set of numbers that both have meet the condition greater than 10 and the condition less than 25. So how do we do that? We can create two logical vectors maybe to make this clear. So numbers greater than 10, and condition .2 is numbers less than 25. And these are each logical vectors, right? So we can, display that for each of them. But now we can sort of create the set of conditions that we want is where they both meet, or both vectors have true. Okay, so if we can do that, simply by typing here, and notice the cases where we have true in both, okay? And then what we can do is we can subset the original numbers vector with condition .1 and condition .2, okay? And we can extract from that vector the values that are both greater than 10 and less than 25 here. Okay, I'll let you play around with understanding that a little bit. If you want to slow down, maybe go back and review this a little bit. But this is an important skill and something that I will want you to learn for this class as we go forward. So these are just really just some quick hitting things that I want you to be aware of. Frequently we're working with two sets of numbers in our analysis, and we want to know which values intersect. So if we create sort of a series of numbers here, 1 to 3, second series of numbers, say 2 to 4, we can get the intersection of those two sets of numbers, which are of course 2 and 3. We can do this, apply this similarly to the union operator, or function, set diff, set equal. I'll speak to you a little bit about this sort of special operator here later in the lecture. So also want you to be aware of how to work with text a little bit in R. Sometimes R maybe isn't best suited for text. Languages like Perl are much more efficient in working with text, but we do have to use text frequently in R, and sometimes you don't want to have to jump to another language just to process some simple text manipulations. And so I just wanted you to be aware of a few examples of how to work with text. So here we have two human genome sequence samples, NA1235 and NA1257. here what we can do is create, if we wanted to, say, append some two-lettered code to the end of those sample names, we could do paste. Let's say we wanted to append it with the genotype sort of extension, and we use this separator operator function here to append then GT to each of these two character strings. So lots of operations here. We have substring, string split. I won't go into detail here. We have pattern matching with grep. So here I've already typed in a set of what we call STRs, or short tandem repeats. And let's say that we had a vector of sort of separate short tandem repeats, and we want to extract all of the short tandem repeats that have the A or T in them, so that we would not want to match this TC tandem repeat. So in this case, we can let's see, I forgot to add the SRS argument here. So here we put the pattern match here, the pattern we want to match against AT, the vector of short tandem repeats, and then value equals true means we want to actually return the value. Notice that the default of grep in R without the value option is the index positions in the original vector. So the index positions were 1, 2, and 4 that had an A and T in them. Okay, so that's the default. We have a third way of using grep. It's called grep-L. Grep-L simply returns a logical vector. Okay, so grep returns the indices of the positions that match the pattern that we're interested in matching. Grep-L returns the true or false logical vector, and grep with value equals true actually returns the elements themselves. Some other functions you may want to become familiar with is the sub and gsub. And finally, I'd like to just show you a very tricky and interesting operator here in R called the in operator. I'll just show you quickly how I frequently use it. It works very well for doing sort of matching operations. So if we want to count the number of adenines again in this vector here, I've already shown you one way, which is to use the string equality. Well, another way that turns out to be quite flexible is to use the in operator. So what in is doing is saying for each element, okay, in this vector here, what we want to do is ask, does that element match an element in this vector, which is now in this case just a single element vector, and then it will return true or false. Does this element match that? In this case, the A. Does this element match A, etc.? And what happens here is that we end up getting a logical vector in return, which we can sum the true values, as I've already shown you how to do, and we end up with the counts for the number of adenines in this particular set of nucleotides. So let's just quickly do that just to convince you that that this is in fact how things are working. So let's just simplify here, and we end up with what we expect, which is that there are 2 adenines in this vector here. So this returns a logical vector of trues and falses. Do they match this value here? And then we're summing the number of trues using that interesting property of the sum function when you're working with sum on a logical vector. Okay, so anyway, play around with that a little bit. just introducing you to a few different ways to work with character data. So just quickly here, frequently you have the need to combine data frames. You can use what's called cbind to bind columns. Okay, so here imagine you have two data frames that each have 10 rows. One has 3 columns, the other has 4. If those rows are matching, say they're all the same positions in the genome, but you have, in one data frame you have 4 columns of data, the other you have 3 columns of data, and you want to just simply join the two together, you can use cbind to bind them column-wise so that you will now have 7 columns of data with the same number of rows. Similarly, you have what's called rbind, so you can bind together by rows. Again, here, assuming, say, that you have the same number of columns in 2 different data frames, maybe the first has 2 rows, the second has 3 rows, you can bind them together and now have 5 rows of data with the same number of columns as you originally had in each of the original data frames. Split is another command here that I use frequently in data analysis. Perhaps we'll come back to this, but imagine you had a data frame here with a chromosomes column. Okay, so that just had, say we're working with SNP data, and we have, each row is a separate variant that has a chromosome position and coordinate, and we simply can break up the data frame into chromosomes by splitting it on the chromosome column. Okay, so here if we split the data frame on the chromosome column here, remember the comma here, rows go to the left, columns go to the right, so this is indicating the chromosomes column. We split using the F argument. We specify the column we want to split on. What this will return is a list of data where each data frame will occupy a different element in that list. So the original data frame is being broken up into multiple data frames where each data frame corresponds to a chromosome, and they are stored separately as elements of a list. Okay, that sounds complicated. It's actually not. When we play around with it with some examples, I think it will become quite apparent that this is a really useful way of simply just breaking up a chromosome based upon some factor. So finally here today, what I'd like to introduce you to is how to write your own functions. This is particularly useful for very repetitive tasks or operations that you're doing over and over again. Sometimes it's very useful to write a function so that you don't have to type over and over again the same operation. It's also really important when you're starting to write more complicated code in your bioinformatics analysis that you develop the skill of writing your own functions, because it allows your code to be interpretable both by you when you come back to it, say 6 months later after you've written it, or with colleagues to which you might share your code. So let's just write a function here quickly called countBase. This is the syntax here. We're assigning this function to the to a new function called countBase. So a function here is no different than the functions that we've been using, previously, right? So we've used the sum function, for example. We've used the set working directory or set WD function. We've used the cat function. We've used many functions here, cbind, rbind. We're simply making our own function now called countBase, and we're assigning to countBase a function called that has 2 arguments, the base and the sequence. Okay, and what the function is returning is the count of bases in a particular specified sequence. So let's imagine that we want to count the A's using this function. So let's go and just illustrate this really quick. So here, sometimes when you're working across lines, it becomes useful to write in the scripting window here. We'll make a function here with the base and the sequence. The black brackets here just indicate the beginning and end of the function. We're just going to do a simple one here using the string equality operator here, which I've already introduced you to. So here we're making a generic function now. We can execute it by highlighting here in RStudio. This is a really nice property of R. We don't actually have to go save this to a file and then source the file. What we can do simply is to execute that little bit of code. We now have defined the count base function, and so now what we need to do is simply provide a base, provide a sequence of bases, so there are two add-means here, and if we simply then execute the count base function, you can see that it returns the value of 2. So by default, what R does is when it simply returns the very last value that was calculated back to the count base function. Another way of being more explicit is to say, define a variable here, say counts, and then we can do return counts. We can then execute this again here so that the function is now updated. We can now do count base. Let's try a different one. Oops. And in the end, sorry about that. We end up with 1 here because there's 1 T here. So all this, what I'm just showing you here is that you can return explicitly a particular variable, or the default behavior in R is to simply return the last value that was calculated. So anyway, I'll let you review this a little bit. This might be something where you take a crack at writing your own function. Perhaps in next week's or week 4 homework, I'll make a small assignment that will get you writing your own function, because this is a really useful skill. So with that, I'd like to just close this series of lectures on the very most basic sort of operations in R, and we'll continue next week working on R and begin to talk about some of the bioconductor packages. So with that, we'll close, and I'll see you next time.